Okay, so today we're looking at section 4.1. Section 4.1 is about probability distributions. So, whenever we perform a probability experiment, we get an outcome. For instance, if I roll a six-sided die, the outcomes are either are the numbers 1 or 2 or 3 or 4 or 5 or 6. Those are the possible outcomes. When I flip a coin, the outcomes are heads or tails. Sometimes those outcomes are numerical counts or measures, like in the case of rolling a die, we get a number. Whenever that happens, whenever that's the case, the outcome is called a random variable. So let's go ahead and get a definition of a random variable. A random variable x represents a numerical value associated with each outcome of a probability experiment. So when we talk about these random variables, they break down into two different types. And you have to be able to tell the difference between the two types of random variables. The first type of random variable is a discrete random variable. And for a discrete random variable, it's one in which there are only a finite or countable number of possible outcomes. Then there's a continuous random variable. And in a continuous random variable, that's one in which there are infinitely many possible outcomes. Okay, so discrete means there's finitely many outcomes. Continuous means there are infinitely many outcomes. So we're going to take a look at an example. We're going to take a survey of gas tanks. And we want to figure out the amount of gasoline present in each one of those tanks. So we're going to measure it and we're going to record the answer. The amount of gasoline represents the random variable, right? It's going to be a number, right? How many gallons? Is it 2.3 gallons? Is it 5.8 gallons? That's a numeric answer, so this is definitely a random variable. But what we want to know is this a discrete random variable or a continuous random variable? Think about that for a second. The amount of gas in a gas tank, would that be discrete or continuous? And when you're asking yourself that question, you're really asking yourself, is there only a finite number of possible answers, or is there an infinite number of possible answers? So, with this gas tank problem, it turns out that it's continuous. Now, most people think of a gas tank and they think, oh, there's, I have a 17-gallon gas tank in my car, so how could there be an infinite number of possible outcomes? Well, it all depends on the measurement, right? When you measure the amount of gasoline in the tank, there are infinitely many possible measurements. For instance, it could be 10 gallons. It could be 10.1 gallons, 10.14 gallons, 10.143 gallons, 10.1437 gallons. There's no end to how many different possible measurements there are. So that makes that continuous. Let's look at another example. A local supermarket records the number of customers who entered the store. The number of customers represents a random variable. Obviously, it's a number. Is it discrete or continuous? Think about that for a second. Are there an infinite number of possible answers or only a finite number of possible answers? And so with this supermarket problem, this is going to be a discrete random variable. All right? You're counting the number of customers. So there's only finitely many possible outcomes. You couldn't have an infinite number of people walk through the doors of a grocery store. It's not possible. Okay. So we have a note. Whenever you're dealing with quantities that are counted, it's discrete. Whenever you're dealing with quantities that are measured, it's continuous. So in this chapter, we're going to be focusing on the discrete random variables, the ones that are are finite. There's a finite number of answers. So previously we looked at frequency distributions, which detailed data entries and their number of occurrences. We can kind of take this same idea for ourselves and use it to work with discrete random variables. And when we do that, we get what's called a discrete probability distribution. So let's kind of flesh out that idea of the discrete probability distribution. What a discrete probability distribution is it's a table wherein each possible value of the random variable is listed along with its probability. A discrete probability distribution must follow these rules. First, all the probabilities must fall between 0 and 1. And then second, the sum of all the probabilities must equal 1. We had seen both of those conditions before when we talked about probability in Chapter 3, that any probability value has to be between 0 and 1, and when you look at the entire sample space, the probability has to add up to 1. When you're looking at one of these discrete probability distributions, they're basically relative frequency distributions. And so that means we can graph them with relative frequency histograms. Okay, so we have an example. In this example, the Human Resources Department at a corporation conducted annual performance reviews for all its employees. Each employee was rated on a 5-point scale, 5 being exemplary performance, 4 being above average, 3 being average, 2 being below average and the employee needs improvement, and 1 is unacceptable performance and the employee is on probation. The results are shown in the table below. Create a probability distribution for this information. Okay. So let's take a look at our solution. We've got 200 employees being evaluated. We want to compute each probability. So the probability that an employee gets a 1, well, according to the table, there were 6 employees that got a rating of 1. So 6 out of 200, because there were 200 total employees being evaluated, 6 out of 200 is 0.03. The probability of being rated at a level of 2, there were 20 employees at a rating of 2, so 20 out of 200 is 0.10. A rating of 3 had 64 employees, so we get 64 out of 200. A rating of 4, there were 72, so 72 out of 200, which is 0.36. And for a rating of 5, there were 38 employees, and 38 out of 200 is 0.19. So when we build a probability distribution, it looks like a frequency distribution. But normally with a frequency distribution, we write those distributions vertically. With a probability distribution, we tend to write it horizontally. So we'll put our value of x on top and our value for the probability of x on the bottom. And we get a table that looks like this. The values of the x's, 1, 2, 3, 4, 5 across the top, and their probabilities underneath, 0.03, 0.10, 0.32, 0.36, and 0.19. From this information, we can make a histogram. And so the way that this histogram is going to look, we're going to have each bar centered at the value of the random variable. So you'll notice you have a bar centered at 1, a bar centered at 2, centered at 3, centered at 4, centered at 5. And remember, with our histograms, our adjacent bars have to touch. And the height of our bars represents the probability. So you'll see that that bar at 1 only goes up 0.03, whereas the bar at 2 goes up to 0.10. The bar at 3 has a height of 0.32, and the bar at 4 has a height of 0.36, and then we dip down at the bar of 5 to a height of 0.19. So this would be your probability histogram. One thing you want to notice about these histograms is that each one of those bars is a rectangle, and the width of that rectangle is 1, the height is the probability. And so if you remember how to find the area of a rectangle, area is always length times width. So if the width is 1, because these bars are 1 unit across, and the height is the probability, the area of each bar will actually end up being the probability of that entry. Now that's not a big deal right now, but coming up in the future, especially when we get into chapter 5, we're going to see that there is this intimate relationship between area and probability. And we're going to use that relationship to help us answer a lot of questions. So next up, we've got a practice problem. And in this practice problem, we have parents of 5th graders at a local elementary school. They're going to be surveyed as to the number of children in their families. The results are listed below. Create a probability distribution and frequency histogram. Okay. So for X is how many children there are in their families. So there were 24 families that had just one child, 57 families that had 2, 48 families that had 3 children, and 21 families that had 4. You may notice that there's no families that have 0 children, and that's because this survey was given to parents of 5th graders. So if they're parents of 5th graders, they have to have at least one child. So don't fret that you don't see a 0 here. There wouldn't be one in this particular problem. So we're going to create a probability distribution and a frequency histogram. So you can pause the video right now, give yourself an opportunity to work out that problem, and when you're all finished and ready to go, just restart the video. Okay, let's take a look at our solution for the practice problem. If we add up all of the frequencies that we get from the frequency distribution that we're given, they all add up to 150. So that means there were 150 families surveyed. So we're going to take the values from the table and divide them by 150 to get our probabilities. So the probability that a family had just one child is 24 out of 150. The probability that they had 2 children is 57 out of 150, which is 0.38. The probability that they had 3 children is 48 out of 150, which is 0.32. And the probability that the family had 4 children is 21 out of 150, which is 0.14. So again, we're going to create our probability distribution, and remember, it goes horizontally. All right, so we list our x's across the top and the probabilities beneath them. And you'll notice that we're fulfilling all of those requirements that the probability distribution has. Remember that each probability has to be between 0 and 1, 0.16, 0.38, 0.32, 0.14, all fall in that range. And if we were to add them up, we'd see that they add up to 1. Okay, you can try that on your own. Okay, so let's make a histogram for that. So again, our bars are going to be centered at the value of the random variable, and the height of the bar is going to correspond to the probability. So our histogram looks like this. And just, I'll mention it again, the area of each one of those bars is the probability. Area is the probability. Okay, so now we're going to turn our attention to some of those values we found in the past, the mean, the variance, and the standard deviation. And we want to be able to do that for probability distribution. because the probability distribution is so much like a relative frequency histogram, we should be able to find those values for this probability distribution as well. So we'll start by giving a definition of the mean. So to find the mean of a discrete random variable, what we do is we take each data value times its probability, and then we add up all those products. So mu equals the sum of x times the probability of x. So let's do an example. The example is we are going to have a probability distribution. It's actually the probability distribution that we just had in the practice problem. And we want to find the mean for this probability distribution. So what I'm going to do is I'm going to take the table that we have here and I'm going to expand it. Okay. So because I need a row for multiplying each data value by its probability. In that first row, or column, we're going to get 1 times 0.16, which is 0.16. In the second column, 2 times 0.38 is 0.76. In the third column, 3 times 0.32 is 0.96. And in the last column, 4 times 0.14 is 0.56. So according to the formula, we're supposed to take this last row and add them all together. So mu equals the sum of each x times its probability. So that's going to be 0.16 plus 0.76 plus 0.96 plus 0.56, which adds up to 2.44. So if you think about this value in the context of the problem, 2.44 represents the average number of children per household. So there's about a little less than 2.5 children per household. So we got a practice problem here for you. Same idea. We've got a probability distribution, and I'd like you to find the mean. So at this point, pause the video, give yourself a chance to work it out, and when you're ready to resume, just hit play. Okay, so let's take a look at the solution for this practice problem. Again, I'm going to add in an extra row to my table so that I can have a space to put my x times the probability of x. So in my first column, 1 times 0.07 is 0.07. 2 times 0.16 is 0.32. 3 times 0.29 is 0.87. 4 times 0.31 is 1.24. 5 times 0.14 is 0.70. 6 times 0.03 is 0.18. Now you may be asking yourself about that fourth column where you see a value of 1.24. You might say, but that's bigger than 1. That's not a problem. It's the probability that has to be between 0 and 1. When we multiply the probability by another number, all bets are off. That number can be larger than 1 at that point. So now we're going to take these values and add them together. So we're going to take 0.07 plus 0.32 plus 0.87 plus 1.24 plus 0.70 plus 0.18. And when we add those all up, we get 3.38. Now, in the last problem, I gave you a little bit of context because that frequency distribution had come from a practice problem where we knew the situation dealing with a survey given to parents of fifth graders. This one we were just given the probability distribution, so there's not really any interpretation that we can make other than 3.38 is the average of these values. Okay. So now we need formulas for the variance and the standard deviation of a discrete random variable. And so we'll look at the variance first. The formula for the variance is given by sigma squared equals the sum of x minus mu squared times the probability. Now, you may notice some similarities there with what we've done in the past. When we found the variance before, what did we do? We took each deviation and we squared it, and then we added them all up and we divided by the size of the sample. Oh, I'm sorry, or the size of the... Okay, so now we want to be able to find formulas for the variance and standard deviation of a discrete random variable. So we'll start with the variance. The variance of a discrete random variable is given by this formula. Sigma squared equals the sum of x minus mu squared times the probability of x. You may notice some similarities with what we've done in the past when we were talking about variance and standard deviation. In the past, what we would do is we would take the deviations, which is the x minus mu, and we can see that here in this formula. We would square them, and we would add them all up. So we see some of that here in this formula. In the previous formula, we would then divide it by the size of the population, or 1 less than the size of the sample. In this probability version, we're multiplying times the probability. Okay? And remember, since probabilities are less than 1, that's given us the division that we would normally have in our variance process. Now, we mentioned in the past that no matter what situation we found ourselves in, when we find the standard deviation, we would always do the same thing. And what we said is we always take the square root of the variance. Well, that's true here too. So for the variance, or for the standard deviation of a discrete random variable, we're taking the square root of the variance. So we've got the square root of that formula that we just saw. All right, so let's look at an example. And in this example, we've got a probability distribution. And if you add up all those probabilities, you will see that they do, in fact, add up to 1. We want to find the mean, the variance, and the standard deviation for this probability distribution. Okay, so we'll start with the mean. We've been doing that in the last example and practice problem. We're going to add in a row to this table for the x times the probability. So 1 times 0.14 is 0.14, 2 times 0.27 is 0.54, 3 times 0.41 is 1.23, 4 times 0.09 is 0.36, 5 times 0.06 is 0.30, 6 times 0.03 is 0.18. And so to find the mean, we're going to add up that last row. So we take the 0.14 plus the 0.54 plus the 1.23 and so on. And when we add all those up, we get 2.75. This value is important because if you look back at the formula for the variance and for the standard deviation, each one of those formulas involves this mean. So we need to calculate the mean before we can do any of the other things. So now I'm going to build a much larger table to find the variance. And once we find the variance, remember the standard deviation is easy. We just take the square root of whatever answer we get for the variance. So the table that I'm going to build looks like this. So now I've got my x's and my probabilities. I'm going to have a column for my deviations, my x minus mu's, then a column for their squares, and then a third column where I take those squared deviations and multiply them by the probabilities. So we'll start with x minus mu. If we take the x value of 1 and we subtract the mu, which was 2.75, we get negative 1.75. And 2 minus 2.75 is negative 0.75. 3 minus 2.75 is 0.25. 4 minus 2.75 is 1.25. 5 minus 2.75 is 2.25. And 6 minus 2.75 is 3.25. Now we have to take each one of these values and square them. So I'm going to have to take the negative 1.75 value and square it. And that gives me 3.0625. If I take negative 0.75 and square it, I get 0.5625. Squaring the 0.25 gives me 0.0625. 1.25 squared is 1.5625. 2.25 squared is 5.0625. And 3.25 squared is 10.5625. Remember, when you're squaring your deviations, those answers should all be positive. We never get negatives when we square these. We never get negatives when we square negatives. So now we have our last column. The last column is for multiplying the column that we just did by the probability for that particular value of the random variable. So in this last column, I'm going to take the 0.14 times 3.0625. And if we multiply that out, we get 0.428750. If we take the 0.5625 times the 0.27, we get 0.151875. If we take the 0.0625 times 0.41, we get 0.025625. If we take the 1.5625 times 0.09, we get 0.140625. If we take the 5.0625 times the 0.06, we get 0.303750. And then if we take the 10.5625 times 0.03, we get 0.316875. Okay, so that's a lot of numbers in the table. According to the formula for the variance, we're supposed to take this last column of the table and add those values up. What's nice about this formula for the variance of a probability distribution is that there's no division in it, right? The division is actually all wrapped up in that probability. So we don't have to do any extra divisions like we would in the past. So we're going to take that last column and add those numbers up. So the 0.428750, 0.151875, 0.025625, and so on. And we'll just do this old school, right? That first column, we add it up, we get 20. So we put down a 0 and we carry a 2. 2 plus 5 is 7, then 14, 16, 18, 23, 30. So we put down a 0, we carry a 3. 10, 18, 24, 30, 37, 45, and we carry a 4. 12, 13, 18, 21, 27, we carry a 2. 2, 4, 9, 11, 15, 16, we carry a 1. 5, 6, 7, 10, 13, so we put down a 3. We carry a 1, and when we add that, we get 1. Drop our decimal. And so this value is the variance, 1.3675. We don't need those zeros at the end. Okay, that was the hard part, right? Remember, finding the variance always has the most work in it. Now what we want to do is find the standard deviation. And to find the standard deviation, we're just taking the square root of the variance. So we're taking the square root of that 1.3675 number. And that's going to approximately equal 1.1694. Okay? So that would be the standard deviation. Finding the standard deviation is easy once you have the variance. Now that process for the variance is a little bit time consuming, a little bit detailed, a lot of long decimals in that process. There's actually an alternate formula to help us find the variance. And it looks like this. The variance of a discrete random variable is also given by, this time it's the sum of x squared times the probability of x. So we take each value of the random variable and square it, then multiply it by the probability. We add those all up, and then after we've got that sum, we subtract the square of the mean. Okay? And there's an algebraic algebraic process by which we can turn the other formula that we had into this one, but that's not important for your notes, so I'm not going to put it up here, but just know that it does convert from the old formula to this one. What's nice about this one is, in general, this one is going to result in a lot less decimal. Okay, so in the previous example, we had a bunch of decimals that were 6 decimal places. That's not going to happen here. We're actually going to do the exact same problem. And to do it, we're going to make a slightly different table. So again, here are my 6 values of the random variable, and here are those probabilities. These are exactly the same as in the last problem. You'll notice that now, instead of having 3 extra columns, I only have 2 extra columns. 1 column for x squareds and 1 column for x squared times the probability of x. So x squared, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, then 25, and 36. Now we're going to take those x squareds times the probability. So 1 times 0.14 is 0.14. 4 times 0.27 is 1.08. 9 times 0.41 is 3.69. 16 times 0.09 is 1.44. 25 times 0.06 is 1.50. And 36 times 0.03 is 1.08. So now what we're supposed to do is we're supposed to add up that last column, the x squared times the probability of x. So we're going to add up the 0.14, 1.08, 3.69, 1.44, 1.50, and 1.08. Those add up to 8.93. In our formula, though, there's also a mu squared. So we're going to have to find the value of mu squared. Remember, we found that mu was 2.57, so we're taking 2.57 squared, and 2.57 squared is 7.5625. And so these last two answers we got, the 8.93 and the 7.5625, we're supposed to subtract those according to the formula. Right? It says take the sum of the x squared times p of x's, which was 8.93, and subtract the square of the mu, which is 7.5625. And when we subtract those, guess what we get? 1.3675. That was the same variance that we got when we used the other formula. So you're going to get the same answer. And then, of course, to find the standard deviation, you would take the square root, and that's going to come out the same as well. So in general, this formula has far easier calculations than the first one. Okay, so a topic that's very closely related to probability distributions is that of expected value. So we'll define the expected value of a discrete random variable. The expected value of a discrete random variable is equal to its mean, which means that the expected value of the random variable x is mu, which is the sum of x times the probability of x. You may be wondering, what does this mean? What is that telling us? Well, an example might help clarify that. So, a local raffle has three top prizes: $10,000, $5,000, and $2,000. There were 10,000 tickets sold for $5 each. You buy one ticket. What is the expected value of your gain? So, if you are the institution that is running this raffle, then how much do you expect to make? And most of the time, when we figure out expected value, we're not figuring out the entire amount that we're going to make. We're trying to figure out how much are we making per ticket, right? If we're selling that ticket for $5, how much of that money is profit to us? So we have to think about what gain means. Gain is generic. We always kind of think of the word gain as we're getting something. It's a positive thing for us. But in this context, gain is used whether we come out ahead or behind. So in the cases where we lose money, our gain is negative. In the cases where we make money, then our gain is positive. And everything we do is relative to the gain. So think about this. If you buy a ticket and win the top prize, right? The grand prize was $10,000. If you buy a ticket and win the $10,000 prize, what's your actual gain? Did you gain $10,000? The answer to that question is no, you didn't. And the reason that you didn't gain $10,000 is because you had to pay to play. Right? So your actual gain is $9,995 because it's the prize money, the $10,000, minus the $5 ticket price. So we're always thinking about gain in terms of what did we get minus what we had to spend to achieve that. Okay. So in this process, we're just going to find the mean, but the x values, the values of the random variable, are going to be the gain values. Okay, so when we create our table, our probability distribution table, the x values are going to be your possible gains. So if you were to win the $10,000 prize, the gain on that ticket would be $9,995. The $5,000 prize would result in a gain of $4,995 when you take away the $5 that you paid for the ticket. And a $2,000 prize would result in a $1,995 gain. Now, if you bought a ticket and lost, then your gain's negative. So if we bought a ticket and we didn't win any of the prizes, our gain is negative $5. Now let's think about the probabilities of each one of those. One of the tickets out of those 10,000 tickets that we sold is going to be the grand prize winner. So the probability that somebody wins that gain of $99.95 is 1 out of 10,000. The probability that they win the $5,000 prize and have a gain of $49.95 is also 1 out of 10,000. Now, sometimes people will ask, why isn't it 1 out of 99.99? And the reason is we don't know what order these are drawn in. Right? So we don't know that this prize is drawn first and that one's drawn second. All we know is that 1 out of the 10,000 tickets will win each one of those prizes. And 1 out of the 10,000 tickets wins the $19.95 gain. So we see those probabilities are all pretty much the same. But the probability of having a losing ticket is not the same as the probability of having a winning ticket. So as you can see from the table that we've set up so far, 3 tickets are winners. There were 10,000 tickets sold. So that means that there were 9,997 losing tickets. So the probability that you bought a losing ticket is 9,997 out of 10,000. Then we're supposed to multiply each x times its probability. So I take the 99.95 times 1 over 10,000 and I get 99.95 over 10,000. 49.95 times 1 over 10,000 is $49.95 over 10,000. $19.95 times 1 over 10,000 is $19.95 over 10,000. And then negative 5 times $99.97 over 10,000 is negative $49,985 over 10,000. We're multiplying that 5 to the numerator of the fraction, to the 99.97, and the bottom is staying the same. To find the mean now, the expected value, remember, is the mean. We're going to add up that last row. So we take the 99.95 plus the 49.95 plus the 19.95 minus the 49.985, and we get negative 33,000. Since these had a common denominator, it's all over 10,000. And if we divide that, we get negative 3.30. That is the expected value. So that means that the average loss per ticket is $3.30. So if I'm the person throwing the raffle, I find this expected value, and that tells me how much each ticket is going to contribute to my organization. Because if the player is losing $3.30 per ticket on average, then that means my organization is gaining $3.30 per ticket on average. Okay, so we've got a practice problem for you. A similar kind of problem. We have a local raffle. There's 4 top prizes. $1,000, $500, $200, and $100. There were only 3,000 tickets sold here, and they were only $1 each. You buy 1 ticket. What is the expected value of your gain? So I know it says example at the top. It should say practice problem. So work this out and go ahead and pause the video. And when you're ready to resume and find out the answer, then just hit play. Okay, so let's take a look at the solution. We're going to set up a table similar to what we just did in the previous example problem. The x values are your possible gains. We're going to create a probability distribution. So, with a $1 ticket cost and our top prizes, if we win the $1,000 prize, then our gain is $999. For the $500 prize, the gain would be $499. For the $200 prize, it's a $199 gain. For the $100 prize, a $99 gain. And if we get a losing ticket, then that is a negative $1 gain. The probability that I have a winning ticket to win the grand prize, there's only going to be one of those out of the 3,000 tickets. And same for the $499. 1 out of 3,000. And for the $199, 1 out of 3,000. And for the $99, 1 out of 3,000. Look at those. That's 1, 2, 3, 4 winning tickets. So all the rest of the tickets are losers. So 4 winners out of 3,000 leaves 2,996 losing tickets. So that's the probability that we have a losing ticket, 2996 over 3,000. Now we multiply each x times its probability. For the first one, we get 999 over 3,000, then 499 over 3,000, 199 over 3,000, 99 over 3,000, and negative 2996 over 3,000. To find the expected value, we find the mean. To find the mean, we're going to add all of those values together. So we get the 999 over 3,000 plus 499 over 3,000 plus 199 over 3,000 plus 99 over 3,000 minus the 2996 over 3,000 because that was a negative. We get negative 1,200 over 3,000, which is negative 0.40. So that's a 40-cent per ticket loss. So if I'm running the raffle, then I know that each ticket is going to bring in 40 cents to my organization. Okay, so that's going to bring us to an end of section 4.1. Please look on Pearson for your homework, and have a great day.